So to begin with, today I'm going to talk about discovering business insights with open source machine learning tools. It's all about predicting customer behavior for the growth of your business. One thing I want to say is in this age of LLM, foundation models, generative AI, whatever you call, most of the people are trying to solve their use case using LLMs, generative AI and all, like large foundation models. It's true that they are efficient, they are effective in some way, but they come up with their own set of cost. And that constitutes a whole talk in itself for some other time. Today, I'm taking a step back and exploring some simpler models, simpler time series forecasting models, which can solve some useful use cases for businesses. I would like to give a shout out to my colleague Hema Veeradhi, who is a data scientist at Red Hat, and who was the equal contributor to this project as well. To introduce myself, I'm Surya Pathak, a data scientist at Red Hat. I'm based in Berkeley, California, and you can reach out to me in my email, GitHub, LinkedIn, whatever works. Happy to be connecting with you all. Yeah. So in today's agenda, I'll be talking about why customer growth is so important for anything, for business. And I'll go through some data sources, time series models, model insights, and talk briefly about one model monitoring tool, and I'll wrap this up with the demo. So this project was started actually. The main goal of this project was to predict customer behavior over time for the Red Hat internal products. It's like predicting customer potential for different customers for different Red Hat products. Although the data was private, I cannot share it over here, but the model is open source, and it's adaptive in nature. So when I started this by talking about business insights and customers, I can adapt this model to any other organization. Let's say you have a GitHub, and you have contributors to some projects, and you want to track your contributors over time, and you want to identify potential contributors for your GitHub projects. You can also use this model. You can use this kind of framework. For this particular talk, we have extracted data or generated data using OpenAI credentials just for that. That's all LLM we have used, nothing more. After that, we employed some time series forecasting model. We got some forecasted data. And using those forecasted data, we classified our customer base, or for other use cases, say contributor base, into high, medium, and low potential zones. Now, one of the reasons why this predicting of customer potential is very, very important is it gives you an advantage on which direction to drive your business through. For example, let's talk in terms of GitHub projects or contributors. If you can predict your customer behavior over time, it helps you to it helps you to manage your investment on your projects. It helps you to manage your vacations as well. So manage your resources, manage your investment, and vacations for your projects. If you know what your contributors, when your contributor is active or when your contributor is not active. Or if you can determine these are the high potential contributors and I should not lose them, you can reach out to them, give them offers, or give them good services so that they be in your organization. Or track low contributors seeking help. You can give them help and suggestions so that they move from lower set of low potential zone to the high potential zones. So in this way, you can manage your business or any kind of projects. So for time series modeling, we are using Hema to predict customer behavior over time. Basically, how much a customer spends every month. We are predicting with respect to ARIMA time series forecasting models. So let's move on to the data sets that we have used so far. This is the simplest ideal data set that we have used. The data set is generated using LLMs. So here we have different accounts. So one of the important thing that you need to understand about this kind of data set is it's not one time series data set, it's a multiple time series data sets. Say, for example, you have 50 customers, 50 contributors, or 100, or 200. You have 200 number of time series. And for each time series, you need to make a predictions. And out of that predictions, you need to classify those customers based on their predicted data. So here we have different account name 1, account name 11, different dates. In this case, it's varying with respect to every week. You have the actual value. You can correlate that with the contributor activity over time. You can correlate this with the revenue over time. And this is the predicted value from the ARIMA time series forecasting models. And this is the MAPE score. Now, what is the MAPE score? MAPE, it's basically median or mean absolute percentage error. It's the percentage error between the actual and the predicted value. Now, this is the good set of metrics for evaluating time series forecasting models. If the MAPE value, if the actual and the predicted values are equal, then MAPE is like 0%, very, very accurate, which is an ideal case. If the more the MAPE is, the less accurate your model is. Generally, it is considered, if it is from 0 to 10%, the MAPE is generally considered accurate. If it's from 10 to 20 or 30, it's considered moderately accurate. But if something above that, it's generally considered less of an accurate. So you need to change your model, add up features, do some data pre-processing, and so on. And again, train your model and again predict it. So that's how you go into the cycle of like making your MAPE as accurate as possible. So MAPE is a good metrics to look into to check whether your model is working or not. So we talked about the data set, and now let's talk about time series forecasting models. So here I'm highlighting two basic traditional time series forecasting models, these which are open sourced. And time series forecasting models are basically those kind of models which takes up the data points from the past, and based on that past trend, it predicts the future. You have ARIMA, which is the set of statistical models that caters to the group of standard structure of time series data. ARIMA, it's based on the underlying correlations. One interesting thing about ARIMA is for every kind of time series data, you need to define the hyperparameters to run the model based on autocorrelations and based on autocorrelations of the past values and moving averages of the past values. So for profit, which is somewhat similar to ARIMA, but it's more of an additive model and tries to detect change point. It's more like a curve fitting model. It's developed by Meta. It's an open source model. You can use it. So one good thing about profit is it's easy to use with default hyperparameters. So you don't need to define hyperparameter at each run. It's automatic. And it's, so this is based on a personal experience. I felt that profit works much better when your data is seasonal. So if every season your data is like, have some cycle of cases, then profit works pretty well. ARIMA, you need to define your own hyperparameters, but it worked pretty well for us because we were dealing with number of time series, like for example, 50 time series data, 100 time series data. So in order to run for all the time series data, we chose ARIMA. Now I told you we have multiple number of accounts and multiple number of time series. But for ARIMA, the catch is how to define hyperparameters for each one of them. Now, that is resolved so easily using the auto ARIMA package. With auto ARIMA, it helps you to determine the hyperparameter automatically based on the individual time series data. So here in this curve, you can see the training points given by the blue lines. The orange point is the test set, and the green line, green dashed line at the left-hand top corner is the forecasted points. So how we run our model is, we train our model, and we keep some data for the test set, and see through MAPE if our model working well or not. So here in this plot, we calculate the MAPE of 5.1%, which is pretty accurate for our use cases. Now, I'm again saying this MAPE is pretty accurate, but this also depends upon the kind of use cases that you are in. Sometimes your data is so sensitive that even a 0.1 or 0.2% difference makes a lot of difference. In that case, you need to have a very, very accurate MAPE. But in some cases, some flexibility is fine. So here we have the training set, here we have the testing set, and the forecasted set, these green points. Now, based on these green points, based on this forecasted data, we classify the ultimate customer set into different zones: high potential zones, low potential zones, and medium potential zones. If we move on, so generally, if there is an increasing trend, so one of the ways with which we calculate trend is by calculating the slope of that line. So if we consider slope as the trend setter of that line, then for an increasing trend, you generally get a higher amount of slope. Now, if your data points are not changing the value over time, then that is generally falls under the place of medium slope, which is constant slope. And if your data points is decreasing over time, over the x-axis, then those kind of data points are, then those kind of trend, those kind of slopes are generally in the negative side. And those are considered as low growth slope. So based on these three different classification of slopes, we classified our data, our customer base, into low growth, medium growth, and high growth candidates. You can do the same thing for your GitHub contributors list. You can track your contributors' activity over time, and based on your contributor activity, the forecasted data points, let's say you want to calculate your contributor activity for next month, and next month for the 4 weeks, you see an increasing trend, then that means those particular customer or contributors generally fall into the high contributing zone for the next month. That's the catch. If I see any contribution activity which is constant over time, then those kind of contributors can be regarded as the medium potential contributors. Let's see some of the examples over here. This is the case of low potential customer or low potential contributors. We can assume that way as well. So in this case, we see an up and down phases for this customer or contributor. Sometimes it is high, sometimes it is low. But if we really see the forecasted green points over here, this is the forecast for the next 5 weeks from the testing phase. So which means that for the next 5 weeks, what I'm seeing is this, for this contributor, they are contributing on the lower side, which means they will not be contributing enough. That's what I'm predicting it now. And that's why I've segmented them in the lower category. Now, we should not make this kind of result as the ultimate truth, but this kind of result can be a key indicator to inform the customer success team or those team which is in conversation with the customers or conversations with the contributors. If we see these kind of indicators, like for example, in this account name 45, it's in the low category. We can inform customer success team that so-and-so customer or contributors in the lower category zone, is there any problem with them? They can then check with their customer or contributor and talk about if there is any issue. If it is not, this can just be a false positive signal. Similarly, if we go to the another example, which shows you the high category of customer, this customer or this contributor shows an increasing trend over the period of time, and for the next 5 weeks also, it is seen as an increasing trend. And this also calls for a key indicator or calls for further investigation from the customer success team, which means that if somebody is performing really well, if some contributor is performing well, if some customer is spending well on your product, you can give them some offers, you can give them some perks, so that they can stay there. They can perform much more better way. So I think the main aim is to keep the customer or contributor intact in your projects or intact in your business. So these are the ways which you can track those contributors or customers and just start the conversation if there is any problem. So these kind of plot can be a first-hand key indication to check with them if there is anything. Now, I just said this is the forecast for the, if I go back a little bit, this is the forecast for the next 5 weeks. There will come a time after next 5 weeks, you will again need to run that model again. And after that 5 weeks, again need to run that model so that you will constantly get the signal of which customers are in the lower zone, which customers are in the higher zone or contributors. So it's not a static type of model where you run once and everything is resolved. But it's something like a dynamic model where you run at every interval, every month, every quarter, or every 6 months or year, and reanalyze your contribution. Yes, sir. Yes, yes, sir. So when we run our model, we check our evaluation metrics again. Yes. And that brings me to the next point. So in let's say, if I need to run my model for 12 months in a year, what do? I need to check that evaluation metrics value at each point to make sure that my model is working well. Because what could happen is, a concept of data drift or data might change at some point of time, which might have some effect on the model. So because of these kind of changes, there might be some change, there might be some feature change, there might be some feature missing. So all this kind of thing, if you are running a model at every instant of time, this kind of model monitoring tools will help you to track your model progress. So MLflow is an open source platform for managing ML lifecycle, including model monitoring. MLflow provides a variety of tools for model monitoring. You can track metrics and logs. Whichever metrics you want to track, you can log over there, and it will be logged in automatically. You can visualize model performances. And you can also set up an alert if there is any change in the model performance. Like, for example, if you can also set up an alert for your MAPE values. Like, if you run it, and if the MAPE score is above 10%, then just send me an alert. You can also set up those kind of things with MLflow. If we need to go to, so here's the UI. So this is the MLflow which was deployed in OpenShift in our Red Hat. So here is a simplest example of how can we track these kind of models. So this is the experiment customer growth model, which I have named. And these are the 2 runs. So this is the 2 different runs I have made. So this is the first run, and here's the metrics, the MAPE value that I have pasted over here. Like, this is what I have calculated. This is what we have got from the model running. And if I go back, if I go to another run, here's another metrics, MAPE, which is like 5.3. So there are 2 things changed in between the 2 runs. One is the MAPE score. It's just because it's not the fault of the model, but it's just I've changed the unit. I've changed the unit from 0.5 to percentage. So generally, the MAPE score is from 0 to 1 if it is there. Then 0.5 is equivalent to 50 or like 5% or something, right? So just the unit is changed. So in these two cases, and if, say for example, if you have 10 different runs over here, how should you visualize these things? You can also visualize by creating some kind of chart, let's say bar chart. So if I add this, so here in the first run I have this 5.34% MAPE. In the second run I had like 0.05 MAPE. So these are different values of MAPE. Consider, let's for example, you have 10 accounts or like 100 runs. You can also visualize if the MAPE has surpassed the threshold value or not. So these are some of the cases where we can look into through MLflow or like, yeah, just things. So now, next thing I want to go through is this repository, which is customer growth model. This is our project repository. So this repository, whatever results I have shown you today, is the code is already over here. The two main folders of this repositories are data and notebooks. So in the data folder, you have the raw data, which was generated from using LLMs. And in the process data, you have the prediction data set, you have the label data set, which, so I can show you along the way. So if you go to notebook section, so first notebook is growth model generate data. And if I go over here, this is the growth model generate data notebook. So here you can see how we utilized OpenAI API key to generate a data set, tabular data set for working for this talk, for this model. So you need to supply the API key in environment variable. You need to give it a prompt. So the kind of prompt I gave is like, make sure it's an account number and make sure the date is between January and July, just random. And then I made sure that a couple of accounts have increased amount over time, decreased amount over time, and medium account over time, so as to I can have some variety to experiment with. So this is the kind of prompt I gave it to the model. And so I'm looping through each account and making a request to this OpenAI credentials. So with this request, and there's some data pre-processing steps that I go through, and ultimately I'll get the data set like this. You have the account name, you have account one, different dates, varying weekly, and this is the revenue. So this is the data that I save in the data folder. Once you generate this data set, we move on to model forecasting notebook. In the model forecasting notebook, you import all those packages for time series forecasting, ARIMA package, which is from PMD ARIMA, and mean absolute percentage error. You already have this package over here. So you have this data set first. Now, generally, in a real world situations, you might need to go through a lot of data pre-processing phases. Like, I just want to give a shout out to the talk that happened earlier today about chaos and data tsunami from Cali. They were talking about all those GitHub data, which is so enormous that it's very difficult to at least like manage and make sure it's there, right? So that is some challenge which we go through, and I've skipped that step over here completely. I've just shown you what happens after that. So in this case, to come to this level of data, we need some data pre-processing, we need some feature correlations, or we need to understand the feature importance, which feature is important for this model. So we need to select all those things. Those are there. So here is one of the example where we create our own features, a feature called tenure. So we didn't have this feature in our data set. So how we created this tenure is we assumed that tenure is something for which we have a non-zero value. If a customer is spending that month, then that month is regarded as +1 tenure. If the customer is not spending that much that month, then that month is regarded as a 0 tenure. So that's how we calculated the tenure, and it gets summed over the tables. So it can act as a feature for our data set. And then we go through, so there are 2 stages over here. First is the test, train and test and evaluate. So once we evaluate our model, Then since it's the time series, we retrain our model into the whole data set and then forecast it. So first phase is the actual value and the predicted value. We predicted it for different accounts. Account 1, every accounts are there. So there's like actual value, predicted value. Once we go through this, we calculate the MAPE, and here I've highlighted what's the accurate MAPE, what's the unacceptable MAPE and all. So this is the calculation part of the MAPE. So here we have actual, predicted, and MAPE values. And we now save all those results in the data folder again. Now, once we have the considerable MAPE of like 5%, which is pretty accurate for our model, and this 5% is like the median MAPE that we have used. We want to see how, like, we can see the MAPE at every line, right? How do you calculate the single score for all of them? How do you represent a MAPE with a single score? So to get an average value, we calculate the median. So here we have the model forecasting algorithm, and then we forecasted the data for the future dates, not for the current dates. So once we have the account name, data, and the forecasted value, our next step is to take this data forward to segment the customers into different zones. And for segmentation, we calculated the slopes of the forecasted value. And that is what we have done over here. So in this case, we have labeled the customer potentials based on different forecasted data. So we have the accounts, date, and the forecasted values over here. We calculate the slope here. And based on each level of slope, we level them. And we level in such a way that we defined a threshold for each one of them. So if we consider different values of slope from minimum to maximum, minimum, we take it as 0 percentile. Somewhere in the medium, we take it as 58th percentile. And the maximum, we take it as 100 percentile. We classified slope in such a way that whichever account has slopes less than 30th percentile, we take those accounts as low potential accounts. And for those accounts which have the slope, that value that lies above 75 percentile, then those kind of accounts are considered as high accounts. This is completely based on our assumption. You can have your own assumption. Sometimes you might think that above 60 percentile is a high account. So it's completely based on your assumption. So it's completely flexible. And depending upon your use case scenario, what you want, you can define it your own threshold. So giving the threshold, I classified different accounts into high, low, and medium. So here you have the classification, everything. So once we have this classification results, we can send these results to the customer success team, and they can identify high, low, and medium, and they can recheck their customer, recheck with their contributors, recheck with their customers. In the next case, just a visualization perspective, we try to plot a couple of accounts. Like, for example, this is the high account over here, as we saw earlier also. So this is like the increasing kind of slope. The next is although it shows over the whole range, it shows somewhat of a constant kind of a slope. But for the next 5 weeks, it shows lower, so which means that it is low account for the next 5 weeks. Now, the third case over here, we can see, although it is also similar to somewhat the above one, but for the next 5 weeks, it shows both minimum and maximum. Like, it goes lower and it goes above. So overall, for the next 5 weeks, it shows somewhat of a constant slope. So if you take an average of all of them, it falls somewhere in the middle. It doesn't change. So we take this kind of account as some kind of medium account, where more or less there is a constant slope. So once we have these visualizations, once we have all these results, we can log in the MAPE values in the ML flow. For ML flow, we have to supply, since it's deployed in OpenShift and we need to have some credentials in order to access them, we have to supply the ML flow URL and ML flow tracking token in the environment variable. And once we have that, we can just log in our MAPE values, calculated MAPE values over here, 5.34, into the ML flow login. And if I want to put this into a pipeline, so at every round, it will go through, once it runs this notebook, it will automatically log in the MAPE values in that ML flow segment. So this is how the whole process happens. This is how we can check the model. This is how we can run the model and run at every instant of time. Having said that, I'll go back to my slides now. So demo is done. So one of the main key takeaways from this talk is it's not just for a business use case. It can be used for any kind of time series use case. The main thing that is needed is time series. Another thing that is needed is what do you want to achieve? The main asking the questions, like for example, you have the GitHub projects, you have the GitHub contributors. What do you want to see? What do you want to track? For example, in this case, we can consider metrics like interaction frequency, how often you interacted with the GitHub member or GitHub contributors. Does that interaction helped in the contributors' growth or not? So these kind of feature sets can be added later. And these are some challenges in GitHub. These are definitely some of the challenges in this kind of customer interactions, because a lot of features are there which is very hard to extract. Like if you are running an organization in GitHub and you have to converse with contributors at every now and then is there a method to record that kind of conversation as a metric in a table and add this as a feature set in this kind of model? And if we can add those things, if we can add those features as a feature set, it's much, I think the MAPE will be much accurate in that case. So yeah, thank you. And here are my, I think this is the customer growth model GitHub repo, and the notebooks the links to the notebooks are here. You can definitely check them out, and if you have any time series, you can apply these models to your own time series, and if you have any issue, you can just open an issue in this repository, and we can have a conversation over there as well. Thank you very much, and let me know if you have any questions. Thank you.
Do we have any questions?
Yep.
Hi, thank you for the talk. I'm actually really into time series.
Sorry?
I'm actually really into time series and stuff like that, so I do have some questions.
Yeah.
It's actually my expertise in it. When you compare Arima to Profit, you mentioned that Profit is better at seasonal, but Arima never had to take into account seasonal because there's Arima for it.
Yes, exactly.
Yeah, and then you also mentioned creating features, like feature as in into a new feature to add into the time series?
Yes.
Is that so as far as I know it, regular Arima doesn't take features unless you're using Arima X.
Yeah. So what you're saying is, the first question is, you're saying that Arima does a seasonality, right? So one thing we are not addressing seasonality over here is because our accounts is multiple. So let's say one account has a seasonal base. Another account might not have a seasonal base. So in order to make sure everything works for all of them, like we are running it, right? We cannot run Arima for one and Arima for another, so it's a bit tricky out there. So just to make the matter simple, we cut out the seasonal part. But from the PMD Arima package, Auto Arima, you can adjust the seasonality over there as well. Like if you have a package PMD Arima and you can call the function Auto Arima, in the argument section, there's a seasonal part where you can on and off over there. That's the one. Another thing about your question is, what was that? Like,
it seems like you're adding.
Yeah, feature, right? So that's a tricky part in the time series. So again, in the PMD Arima package, as an exogenous variable, you can add up the features over there inside the argument itself. But the condition over here is if you are predicting for the future where you don't have any value for the feature or the target variable, it's a complicated thing. But sometimes you don't have the values for the target variable, but you might have the future values for the feature variable, right? You got it?
Yes.
Yeah. So in that case, while predicting it, you can supply the feature values as an exogenous variable in the PMD ARIMA package in the time series.
Oh, okay.
Yeah.
So the model isn't like vanilla ARIMA. It seems like they're using ARIMA X, which is like a modified version of it.
Yeah, I think it looks simple. It's like the one direct statement. You just put the argument, you just fill in the boxes, but most of the things goes back end. I think so. Yep. Please take a look. Yep.
Any other questions? All right, I think we had a pretty good group for this late in the evening.
Thank you. Yeah.
Great, thank you. A round of applause, please.
Thank you very much.